This insight about the order of events led elsewhere. Einstein found that in certain circumstances, time can slow down. Any periodic event can be used to measure time. This one, a light beam reflected back to its source, acts like a clock. The spacecraft is tracked by an observer. No matter how fast the spacecraft travels, the speed of the light beam will not vary. At a low speed relative to the observer, the path of the light is vertical. The two clocks run at the same rate. When the relative speed is much greater, the light will be seen to trace a longer path as it moves up and down through space. The speed of the light is constant, but its path is longer. The moving clock appears to slow down. As the relative speed approaches the speed of light, the observer sees the moving clock almost stop. Moving observers will see each other's time slow down. The measurement of time underlies all other measurements. The length of a moving object is not the same as its length at rest. A spacecraft acts as a local reference point. Though it seems slow against the background of the stars, the space freighter is moving by at a very high speed. A clock in its bow is synchronized with one in the stern. The freighter crew, considering themselves at rest, will see the spacecraft pass by very quickly. It takes 22 microseconds. From this and the relative speed, the freighter's crew established the length of their ship. The same event is seen from the point of view of the spacecraft. Microseconds. The spacecraft's reading indicates the freighter is shorter than its crew thinks it is. To those on the freighter, time in the spacecraft is passing slowly. Both are right. Moving lengths contract. Moving clocks run slowly. Space, like time, is relative.
If lengths contract and if times seem to slow down, then we should expect to see some interesting results. And as a matter of fact, there are some striking results in an experiment that was made on this mountain, Mount Washington, in New Hampshire. Let me try to explain how it works. we have cosmic rays that come from outside and hit the very top of the atmosphere, and then they give rise to subatomic particles that are called new mesons. Now, these new mesons are moving very fast, very close to the speed of light, and when you have high speeds like that, you expect these relativistic effects really to amount to something.
Mu mesons have a decay rate established by laboratory experiment. A group of mu mesons decaying at this regular rate can be used as another kind of clock. According to Einstein's theory, mu mesons moving relatively to us should decay at a slower rate. If Einstein's theory is not correct, the decay rate of mu mesons is so fast that even traveling near the speed of light, very few would reach the bottom of the mountain. In the actual experiment, most of them did reach the bottom. The mu mesons' decay rate had slowed down.
Now, that slowing down of their time means that, from our point of view, they live longer. And if they live longer, well, they can come down to the bottom of the mountain. And this numerically explains the effect that was observed, that more reach the bottom than you would expect. Now, however, there's another question, and that is, suppose we're moving with the mesons. Then, if we're moving with the mesons, there's no slowing down of their time or anything like that. How then do we account for the fact that these mesons actually manage to get through to the bottom of the mountain in large numbers? And the answer here is that according to the view that the mesons have of the mountain, there is a contraction of lengths. And the mountain, instead of being this high, for the meson seems to be about that high to them, and they can get through in their short lifetimes. Now, you can explain it a third way, and this is the amusing part of it. Suppose we were moving, not with the mesons, but at, say, half the speed of the mesons. Then there would be a sort of partial slowing down of the time of the mesons and a shrinking of the lengths, the distance they have to go to. And these two effects would combine to explain the same result as before. But we see from this that, in a certain sense, time measurements and space measurements in relativity are such that time and space are completely mixed together. And indeed, we talk of something called space-time, 4 dimensions, which has 3 dimensions of space, 1 of time, and all 4 are more or less on an equal footing. It's important to realize that these contractions of lengths and slowing downs of times are appearances. And I think the best way to illustrate that is take this pen here. If I hold this like that, you see it has a certain length. But now, if I put it like that, it is foreshortened and it looks as if it's smaller. So much so that if I go like that, pointing directly at you, it seems to have shrunk to 0. Now, this perspective effect essentially is what is behind the slowing down of time in relativity and the contraction of lengths. It's an appearance due to the way we look at things. Once we change time and space, we change practically everything that we talk about in physics. Einstein found that mass is in a certain sense relative. An example can be seen in these subatomic particle accelerators that people use in physics.
Particle accelerators are used to investigate the internal structure of the atom. Subatomic particles have low mass at low relative speed. To penetrate a nucleus, particles must be accelerated close to the speed of light. A result of Einstein's theory was that the mass of an object would increase as the speed of light was approached. Mass is defined in terms of motion. This particle has a certain mass. Mass is the resistance of an object to being accelerated. The greater the mass, the more the resistance. The particle is accelerated by an electrical impulse. Each impulse has the same strength. As the velocity climbs, the impulses have less and less effect. The mass is increasing. Close to the speed of light, the mass approaches infinity. In practice, no mass can be infinite because that would require all the energy in the universe.
In the theory of relativity, there's a so-called paradox, which is called the twin paradox. And it goes more or less like this. Suppose I have two twins, and one twin stays at home. The other twin goes traveling out into space with a speed, almost the speed of light relative to the stay at home. And this twin goes to a great distance, then turns and comes speeding back. When the two twins meet again, it can well turn out that the stay-at-home twin is some 20 years older than the traveling twin. How do you account for this? Well, some people try to explain it by saying, oh, it has to do with the slowing down of time with motion and that sort of thing. It really doesn't. Basic to it is the fact that each of the twins ages at exactly the same rate as the other. Well, then you ask, how does the discrepancy come about? It comes about because the two twins have traveled through different intervals in space-time.
There are two clocks, one on Earth, the other in a spacecraft. The star Vega is 25 light years away. We assume there is a clock there synchronized with Earth time. Traveling at 9/10 the speed of light, the moving clock runs slowly. When it arrives, only 2.5 years have elapsed for those on board, while more than 25 years have passed on Earth. When they return, the travelers on the spacecraft are younger by 45 years than the people on Earth. Individual systems, moving relatively to others, have their own time and their own space. We can see the same trip from the point of view of travelers in the spacecraft. They will see Earth and Vega as a single system, moving past them near the speed of light. Moving lengths contract. The stern clock in the moving system will be ahead at this speed by 25 years. The moving clocks run slowly. Only a quarter of a year has elapsed in the Earth-Vega system. Reversing direction, the clock on Earth will now be ahead of Vega's by 25 years. Regardless of the point of view taken, the result is the same. These separate systems do not exist in isolation. They are part of a universal union, space-time. In his search for truth and beauty, Einstein rebuilt Newton's universe. Yet for the ordinary purposes of mortal men, the world is much the same. Time goes on.
Einstein played violin, I played piano, and we used to play duets now and again. And he had a beautiful tone and a very profound, loving understanding of the music. He liked especially the music of Mozart, also Vivaldi and Bach. What he saw in the 18th century composers was a structural simplicity and beauty that was sort of delicate, elegant, and firm. And there was something analogous to that in his own scientific theories. Knowing the man Einstein was one of the most amazing things that ever happened to me, but it's quite impossible to describe it. He didn't mind making fun of himself. For example, he sent a picture of himself to a longtime friend, and on the picture he wrote, "Here's what the old guy looks like now. You feel this horror my peace will shatter? Think, what's important is inside, and anyway, what does it matter?" I've never met anyone like him before or since.